Okay, guys, let's have a look at another example. It says EC is a diameter of circle DEC. So let's have a look at where circle DEC. Here it is, DEC. So EC is a diameter of circle EDC. So that's great. So there's a whole lot of information there. EC is produced to be, alright, so EC is produced down to B here. Okay, and then it says BD is a tangent at D. So BD is a tangent. This line BD is a tangent. There's a whole lot of theorems that can apply there. And then it also says AB is perpendicular to BE. So AB is perpendicular to BE. So we've got a 90-degree angle there. Okay, now it's going to ask a whole lot of questions, but before we do that, let's brainstorm a little bit. Let's brainstorm. What we've got is, and I'm going to use a different color here. Let's have a look at, say, a pinkish color. Do you notice if that EC is the diameter, then obviously that is 90 degrees, that D3, angle in semicircle. Okay. Also, if you have a look at this carefully, if you look at this here, what we've got is we've got the angle between the tangent and the chord equals the angle in the alternate segment. So if this is a tangent, DB is a tangent, and DC is a chord, look at that. So there's your tangent. Let's draw it in. And there's your chord. What do you notice? That's the angle between the tangent and the chord, that's D1, is equal to E. Okay, so that's quite an important thing as well. We've also got this is 90 degrees, so let's draw that in there as 90, and that's very interesting because if you look at this quadrilateral ABCD, if we bring it up there a bit, it must be a cyclic quad because the outside angle there, D3, is B1 plus B2. So it means that this must be a cyclic quad. Okay, and there's a whole lot of wonderful information. Now let's explore what they want us to find. Okay, let's look at the first question. It said, prove that ABCD is a cyclic quad. Well, there we've got it. We've actually seen from the brainstorming that it is. Now, how do we set that out? Well, the first thing we can say is that D3 is 90 degrees, angle in the semicircle. What a pleasure. Angle in the semicircle. D3 is 90 degrees. And then what do we know about the angle B there? Well, we know that angle B1 plus angle B2, the whole angle, is also 90 degrees. That is given to us there. Okay. And so therefore you can conclude that D3 is equal to that angle B1 plus B2, and in that case you can probably agree with me that ABCD is a cyclic quad because the exterior angle, so therefore we can say ABCD is a cyclic quad, and the reason being the exterior angle equals the interior opposite angle. Okay, and there it is, and that's the first piece. So we know that this ABCD is a cyclic quad. So of course now you can assume all the other properties of a cyclic quad because an imaginary circle can be drawn around ABCD. It's a cyclic quad. Okay, what's next on the agenda? Let's have a look here. So we've done the cyclic quads. Now we want to prove that A1 is equal to E. Now remember, you've got a cyclic quad here. So here's A1. Now you know that A1 must be equal to D1 because it's a cyclic quad. That BC there, that line BC, or if it's a circle, there'd be an arc BC, subtends the equal angles in same segment in the circle. Okay, but this is a cyclic quad, so we can assume that A1 is D1. And we've got and then if you go up, what do you know about D1 is equal to E because of tan chord. The angle between tangent and chord is angle in alternate segment. So automatically you can see that A1 is equal to E there. Look at that. So let's write out the proof. I love this geometry. So what do? Let's start with A1. We can say A1 is equal to D1. Reason being because that line or arc BC subtends equal angles at the circumference there. But in other words, A1 is equal to D. So you could draw the circle through there. We're not going to do it, but we know that that's a cyclic quad. So A1 is D1. But then D1 is equal to E. So we can say, but then you can immediately conclude that therefore rather not therefore, let's rather say just but, or you can also, if you want to write but, you can. But we know that angle E is equal to D1 as well, and that is the tan chord theorem. So D1 is equal to two angles. It's A1 and E, so therefore A1 is equal to E, exactly what we wanted there. So that sorts out number B there. Okay, now what about number C? Ooh, BD is equal to BA. Okay, I'm going to use a different color here. We've got BD, let's just draw that in. BD is equal to BA. Okay, now that means we're looking at an isosceles triangle. So we want to prove that these two sides are equal. So what does that mean? We need to prove that D2, the angle D2, and the angle A1 and A2, that those two are equal. So you want to prove that this angle here is equal to this angle here. Well, let's have a look at this. Okay, what do we know about D2? Well, it's most definitely equal to D4, vertically opposite. Now remember, this is a tangent here. There's a tangent here. So the angle between the tangent and this chord, let's bring that circle into view. The angle between the tangent and this chord is equal to the angle C3 in the alternate segment. But this ABCD is a cyclic quad, so C3 is A1 plus A2. That's the exterior angle of the cyclic quad. And there we've got it. So we immediately then can conclude that D2 must be equal to A1 plus A2. So we start with D2. So it works kind of like this. You've got D2 is going to equal D4, and then D4 in turn equals C3, which equals C3 there, and C3 is equal to that whole of angle A1 plus A2. So immediately you can conclude that. So let's build up the proof. So what did we do? Let's start with D2, and it equals D4. So we've got number C. We can say that D2 is going to equal, what would that be? D2 is equal to D4 there. Vertically opposite angles. Way to go. Vertically opposite angles there. Let's just check it out again. You've got D2 is equal to D4, correct. D4 is C3. Why is that? Tan chord. So we've got, so D4 would then be equal to C3. And that would be, here would be tan chord theorem. Great. So we've got that as well. Then what about C3? And then we know that C3 is A1 plus A2, exterior angle of the cyclic quad. What a pleasure. So you can see now immediately D2 is D4, D4 is C3, C3 is A1 plus A2, and therefore you can conclude, therefore, that D2 is equal to A1 plus A2. And if that's the case, if D1 or D2 is equal to A1 plus A2, if these angles are equal here, these guys here, automatically, what do we know? That those two sides are equal. It's an isosceles triangle. Therefore, we can immediately conclude that BD is equal to BA. So therefore, BD is equal to BA. Reason? Sides opposite the equal angles. Okay, there we go. Sides opposite the equal angles. Okay, there we go. Lovely geometry, this. And then what's the last one? We've got that we want to prove that C2 is equal to C3. That C2 is equal to C3. Now, people watch this. I'm just going to tidy that up a little bit so it looks neater. If you look at this, D2 and C2 are equal. That's a cyclic quad. Look at that. Look at those angles in the same segment. The line AB subtends equal angles. So you've got D2 is equal to C2. But you already know that D2 is equal to C3. You've actually proved that. So a way you could do it if you want to, you could say, well, let's start with C2. C2 is going to equal D2. All right. D2 goes to D4. D4 goes to C3. And there you've got it. So C2 would then equal C3. So let's write that down. So let's start at C2. C2 is D2. What's the reason for that? So I'm going to go to another color here. Number D. So what do we know? We can say that C2 is equal to D2. Now, what's the reason for C2 being equal to D2? So you can say that C2 is D2 because AB subtends equal angles. So there we go, AB subtends equal angles. And then what about D2? D2 is D4. And what's the reason for that? D2 is equal to D4, vertically opposite angles. So let's write that in. Vertically opposite angles there. And then what is D4 equal to? And we know that is equal to C3 because of the tan chord theorem. So let's go and check that. So D2 is D4 and D4 is C3 tan chord, and therefore C3 and C2 must be equal. Okay, so here we go. C2 is D2 to D4 to C3, therefore C2 is equal to C3. What a pleasure this is.